Hi, I'm Samuel Boone from the University of Melbourne and the AusGeochem Geochemistry Network. And today I'll be talking about AusGeochem and the future of big data in low temperature thermochronology. So late last year in 2019, the AusGeochem Geochemistry Network, or AGN team, was formed. And we're a team of expert geochemists from across Australia, based at three different institutions at the moment, three different nodes, one at Curtin University, one at the University of Melbourne, and one at Macquarie University. And we're a subsidiary of AusGeochem and funded by the National Collaborative Research Infrastructure Strategy. Well, we only have three nodes at the moment. We aim to expand in the near future. However, we're already working with geoscientists from across Australia from a number of universities and institutions. And the aim essentially is to, by pooling our resources and our expertise, that we can enable more innovative and important geoscience research to be performed within Australia, and then we can make that science more visible to the wider world. So the chief mechanism by which we aim to achieve these goals is through the development of AusGeochem, an open cloud-based data platform for Australian-produced geochemistry data from around the globe. Essentially, the platform provides a tool to Australian geochemistry laboratories that simultaneously acts as a sample registry, allowing labs and analysts to upload and archive information about geosamples that they've obtained and associated geochemistry data that they've produced. And they can do this in a streamlined fashion, either through the user interface or via an API, which we'll talk about in a little bit. In addition, the platform acts as a data repository, allowing people to, again, store and archive those data. They can disseminate those data to selected colleagues or publish it and make it widely accessible to the public. And finally, the platform also acts as an analysis tool or an analytical tool that allows people to do certain amounts of statistical analyses. They can mine data from within the thousands of data points that are stored and archived within the database, and they can perform on-the-fly data synthesis and visualization. And then at the end, they can export the data that they're interested in, and they can also export the figures and maps and plots that they've generated within the platform. Now, to build this, we've teamed up with Lithodat, who are actually doing the software engineering for us. And in addition to the core model that Lithodat has developed that drives the platform, there's a number of method-specific data models that are currently under development. These include shrimp uranium lead, as well as laser ablation uranium lead and lutetium hafnium, and argon-argon. And in the future, we aim to expand to then also include laser ablation rubidium strontium and samarium neodymium, as well as major and trace element geochemistry. However, there's three other data models that are currently under development, which I'm going to speak about further today. And these are data models for fission track and uranium, thorium, samarium, helium analyses, as well as thermal history modeling generated from those data. And to do this, we've brought together a team of expert low temperature thermochronologists from across Australia, which includes Dr. Martin Danisic from Curtin University, Dr. Stan Glory from Adelaide, Dr. Renji Joe from UQ, Professor Barry Collin and myself at University of Melbourne, and Dr. Fabian Coleman from Lithodat. And we've designed data schemas and data models for fission track analyses, uranium, thorium, samarium, helium, and thermal history models, as I mentioned. And so in addition to the sample information that can be collected and stored within the core model, these data schemas allow analysts and laboratories to upload and archive data that associated with these methodologies that include analytical metadata, detailed analyses on per grain and even per fission track basis. These record crystallographic dimensions and morphologies, as well as chemistry, kinetic parameters, reference material results, and then a bunch of additional information associated with thermal history modeling, such as metadata, input parameters, and goodness of fit, amongst other things. And these are stored in a structured relational database that, which you'll see in a moment, enables users to perform quite interesting data analytics and visualization functionalities. Now, users can upload those data into AusGeochem, quote unquote, manually via the intuitive user interface that's within AusGeochem, and this includes bulk data upload. But they can also take advantage of AusGeochem's application programming interface, or API, that allows them to then write scripts, which can essentially digest a wide variety of different analytical data produced from different analytical software and equipment. And these basically then can be automatically uploaded into AusGeochem via this API, where they can then be shared to collaborators or to the wider public. So here I'll give a quick demonstration how users can interact with thermochronology data within the platform. So you can explore the database in its geospatial context by scrolling around. It operates similar to how Google Earth does. You see here we've just changed the base map from satellite view to street map, but we also have other types of base maps, including geology and dark. Now, if you'd seen, I've just hovered my cursor over a sample. Some small amount of information like sample name comes up, but when I click on it, I can find out additional information about the sample, the associated data, and here we're looking at a range of appetite fission track analyses from around Sydney in Eastern Australia. Now, by clicking on the reference, it takes you straight to the associated publication where you can find out more about the study. So one of the most powerful and exciting features within the AusGeochem and Lithosurfer platforms is the ability to do cross-data analytics on the fly. And here we're drawing a polygon over a number of appetite fission track analyses from southeastern Australia. And you can see here that Lithosurfer is doing some on-the-fly calculations and produces a number of nice figures. Here we're looking at appetite fission track age versus mean track length, or boomerang plot. We can go up and look at age versus elevation. And there's also age histograms. And you can see that you can actually adjust the axes on the fly within the platform. And so this is quite a powerful tool, and then you can export these plots at publication quality standards and plug them straight into your manuscripts, which is quite handy. So scroll up a bit further towards Sydney and Newcastle. You can see that we can turn on other types of data, because of course AusGeochem and Lithosurfer not only house low temperature thermochronology data, but a range of geochemistry and geochronological techniques. And again, we're drawing another polygon in the Penrith area of not only appetite fission track data, but a number of geochronometers. And again, Lithosurfer is making some calculations, comparing these data and producing some plots. And again, so here we'll look at age versus elevation. And what you'll see is that the color of the plots actually are associated or relate to the type of data. In addition to the various visualization and analytical functionalities that I've just displayed, one of the important aspects of these data models and these data schema are the fact that they actually record reference material results. So these are the results that people get on the reference materials that they analyze along with the unknowns when they're generating all of these data. Now, this is important because it allows users of the platform to independently assess the quality of the data they're looking at. So what we're working on at the moment is incorporating a number of ways in which people can visualize the quality of data. So this will include observed versus accepted reference material plots, so one-to-one plots, as you see here in the top left. And in addition, then people can actually start monitoring, or laboratories can monitor how they're doing for certain reference materials over time, over many different analytical runs. So you can see if your precision's changed over time. And then we can perhaps incorporate things like steam graphs, which are fun ways to, and interesting ways to visualize how precision over just one lab, an individual lab, or perhaps multiple labs are changing over time, which could reflect new machinery and new equipment, as well as new analytical techniques. And similarly, we're recording, or you're able to record how well thermal history models produce input data. So you put in a bunch of various input parameters on the left side that feeds into these thermal history models. And then we'll also record the predicted data that those models generate. And then all of this will be uploaded to AusGeochem to allow people to then, again, assess the quality of those thermal history models. The expert advisory group is already employing AusGeochem and these data models to produce novel science by collating over 3,500 fission track and helium data, as well as the associated thermal history models from across Australia. So stay tuned. Now, if you want to find out more about the AGN or AusGeochem, I encourage you to visit their respective websites. You can also see other talks given by the AGN and their collaborators on the AGN's YouTube channel. Thank you very much.